but I'm cross-appointed with math and statistics, and most of my graduate students go through math and statistics. And I also have an adjunct position with community health sciences, public health essentially, which I also have a couple of graduate students in. And the reason I've ended up in this sort of position is because most of the work I do is on infectious disease modeling. I've been doing this for, I suppose, 20 years in some form or another now. But actually, the sorts of models I'm going to talk about today, which are really what you'd term the classic infectious disease models, they're not really models that I work on day to day. I tend to work on the more computationally advanced and in some ways less mathematically interesting models, spatial models and network-based models. So this stuff is not new to me, but it's stuff that's always been in the background and not stuff that I use day to day. So this is something that I've had to brush off recently, because the spatial network models that I generally work on, you need high quality, high resolution data to get anything interesting out of. And we don't tend to have that sort of data for human populations, certainly where epidemics are concerned, but I'll come on to that. The other thing that I should say as well is that tying these departments and faculties together, as well as a few others, is this thing up here, which we call the UCBC, University of Calgary Biostatistics Centre. So we set up this virtual centre across departments, because we have a whole bunch of statisticians working on biological applications, health applications in different departments. And this was a way to bring ourselves together. You may have seen that we've run some workshops and things in the past, which we're going to continue to do, probably via Zoom again in the near future. So this might be a bit of a dummy run for that. And we also set up a graduate program as well, which is interdepartmental, which is going quite nicely, I think. Anyway, I shall, I'll say in terms of questions, I think there are going to be some natural places for me to stop. So if there's something urgent, I'm quite happy to be interrupted and talk about that, but there will be natural places where I can ask Leigh what's come up in the Q&A. Obviously, I will not be keeping an eye on the Q&A as I'm talking. Okay, so this is a biostatistics workshop, obviously. However, the session, well, this morning for me, this first session is not only not really going to have any statistics in it, it's not even going to have any stochasticity in it. Okay, so I'm going to spend the first 2 hours talking about what I've termed these classic models, and we'll focus on the SIR compartmental model, which is really a series of ordinary differential equations. And then I'll talk a little bit about extending those and how some of the stuff or early stuff that we've done in relation to COVID-19. This afternoon, there will be statistics, okay? There'll be a likelihood function and all those sorts of things. But for this morning, we're going to be deterministic. Okay. So I put this slide up. I pretty much do with all of my talks, as some of you will be aware, because this is really what started me on the road to well, my current research career. So I had a postdoc started in 2003 at Cambridge in the UK, working on the foot and mouth disease epidemic of the UK from 2001, which is a livestock disease, no public health implications. It seemed pretty catastrophic at the time because it shut down the UK tourism industry and the farming industry, obviously, and we actually delayed a general election. In hindsight, it doesn't seem like such a major thing at all, but it felt quite major at the time. And for that epidemic, I was really, that data set, I was working on spatial models. Okay, so I'm working on models that are trying to mimic this sort of clustering that you see. So this is actually a simulation rather than the actual data, but you get this sort of clustering by the end of the epidemic, as well as what we term the epidemic curve, right, which has this quite familiar shape. So the reported cases there are actually the number of farms. So we model at the farm level here. The models I'm going to talk about today, well, hopefully I'll talk a little bit about spatial models, but I'm not sure I will get there. The models I'm going to talk about today are going to ignore that, right? They're just really deemed with modeling the temporal pattern of disease, okay, using some mechanistic biological assumptions. Okay, now going on at the same time as my postdoc was the SARS outbreak, and actually we talked about getting involved in that, but didn't in the end. Those sorts of spatial models I used for foot and mouth were not really much use for SARS, right? There's a spatial element to it, obviously, in terms of how it was spread globally. But once it got into countries or cities where the infection really took off, it's very hard to record people's spatial location, especially as they move around. As Patrick, I heard, was saying earlier on, easier to do with animals, right? So the sorts of models I'll talk about this morning were more applicable to SARS and, of course, what we're going through now. So this is the that ubiquitous symbol for COVID-19, picture from the CDC photo library. This is not a workshop on COVID-19. It's sort of more general than that. But as I say, I will go into some of the stuff that we're doing and try to tie some of the ideas back to what's going on now. But I will also mention that, especially with the spatial models and network-based, well, spatial models especially, you can also use these models to model things like invasive species. Right, so this is an example. Emerald ash borer is basically destroying trees all over, and you've got other pests as well doing this sort of thing. And invasive species like giant hogweed and other plants, and you can model their spatial spread using these sorts of models. Okay, so there's a list of diseases, and some of those you may have heard of, some of them you may have not. I mean, a lot of my work has been on livestock diseases, so PRRS is probably not familiar to most of you, but it's a very important disease in the swine industry. The human diseases up the top, I'm sure you're more familiar with. I will make one point about terminology. So we do have this tendency to talk about infectious disease modeling, and what we really mean is communicable disease modeling. Okay, so something like cholera is an infectious disease, but it's not really transmitted between people. It can be, but not very much. It comes from the environment, right? Generally poor quality water. It's still an infectious disease, but cholera is not communicable disease. And what I'm really talking about is models for diseases that can be passed from individual host to individual. But like I say, we can also think about things like invasive animal species or plant species. We've actually used some spatial models to try and model fire spread. This wasn't forest fire. This was actually pieces of wax paper that John Braun was setting alight to in his garage. He does it under more controlled conditions now, I believe. But you could take those models to think about modeling forest fires as well, because the patterns are very similar. And although I've not been involved in any of this sort of thing, people use these models sometimes to try and model memes, viruses, on computer viruses, financial market contagion, and that sort of thing. Okay, so let's hone in on the topic of today's workshop. Well, that says workshop, right? Which is where you buy large frying pans. I should say workshop, obviously. So mechanistic models of disease transmission is really what I'm talking about. And this term mechanistic is quite important. So the idea here is that the models have built into them some mechanism that mimics biological and ecological mechanisms that occur in real life. Okay, so I say biological and ecological because disease spread tends to be, or I shouldn't say tends, it is a function of both the biology of the virus and the host. Like, do you get infected? Is there enough virus getting into your body to actually become solidified? But also ecological in the sense that how the population moves and interacts is also important, right? So these models try to mimic that sort of interaction in some way. The parameters as a result are usually biologically, ecologically interpretable, right? We talk about transmission rates, we talk about recovery rates. So these are not parameters in, say, a linear regression model, which are mathematically often, well, linear, that's quite interpretable. Let's say a quadratic model, right? The parameters there are easy to interpret mathematically, but you know, the squared term is not so easy to interpret in terms of what it will mean in a real system quite often, right? We often go back to the model and think about where the maximum is and what the rate of decay is and that sort of thing, or the curvature, I should say. But the parameters here are interpretable, and that has the advantage that we can often think about in estimating each of them from different studies. And that's what happens a lot in this sort of modeling. Okay? We can estimate them in a piecemeal way. The primary use of these models, I would say, is either to forecast what's going to happen, although I don't tend to like the word forecast because, well, I'll come back to that, but they're usually forecast with a lot of error that it often isn't quantified. But more generally, we're trying to project forward and what might happen if we apply some control strategy to those simulated epidemics, right? So we get an understanding of the system, certainly in qualitative terms, well, in quantitative terms as well, but the mapping to real life can be fraught, as we'll see. Okay. In terms of COVID-19, we're primarily talking about what sort of social distancing measures should we implement, and how long do we keep them, right? How long do we keep schools closed? Who do we allow to go to work? How long do we keep that sort of lockdown in place? So the models, these go back like 100 years plus, they were never, as far as I'm aware, they weren't really derived with the goal of data analysis in mind. But in the second half of the talk, or the second session, we will consider how we're going to inform them via data as well, because we're statisticians. Okay. Now, there's a bunch of other things that we might think about using for analyzing infectious disease data. Okay, so these are data-driven techniques. Okay, so I've collectively termed these disease surveillance methods models, but you could easily think of them as just statistical methods or models. So, for example, we have the process control type methods for detecting when an epidemic takes place, right? So we may have something like cases of measles, and we know that measles is endemic, so you get cases going along, and then suddenly you get an outbreak, right? And so these methods would be used to try and identify as early as possible when that outbreak is taking place, for example. Okay. There are also things like spatial disease mapping, which Patrick is an expert with, and well, very similar, the idea of spatial time series models, where your response is basically the number of cases you've seen, right? Or the number of hospitalizations or the number of deaths, right? And then you've got a temporal aspect and you've got a spatial aspect there. The difference with the mechanistic model is that its primary response is not, or its primary output is not the number of cases that you might see, it's the number of cases that are actually there in the population, which can be quite different things, right? So that's why I would differentiate those two things. And also the time series models, spatial disease mapping models don't really have that mechanistic component to them, right? They're more general. The spatial correlation is a two-way thing, whereas in an infectious disease model, it would tend to be a one-way thing, right? An infective individual infects a susceptible, right? Rather there being a two-way thing. And we can also use things like regression models, etc., etc. Now, I'm not going to be discussing those methods today. They're extremely important, but I'm really going to stick to the mechanistic models. And if I just flick backwards to that foot and mouth slide, one way to think about what the difference between these models is imagine you've got this epidemic curve down here, and we'd only seen up to this point in time, right? So you could use some sort of regression analysis to try and predict what's going to happen next. Looking at that, you would probably predict that that's what's going to happen next, right? There's a linear increase there. Or if you know that the curve's got to come down at some point, you might fit a quadratic, but then you wouldn't capture this sort of pattern there. The models, the mechanistic models of disease spread will inherently produce curves of this shape, right? If the parameter settings are right, they're derived to mimic this. And that's a sort of key difference. They're driven by the biology and the ecology. They're not driven by the data. Okay, but like I say, we will try to tie them back to the data later on. Okay. So, well, actually, is this a good point? Do we have anything on the Q&A at the moment? Can't see anything.
No, Rob.
Okay. Okay. All right. So I'm going to show you a model soon. We're getting there. Right. But before that, just talk about why we want to do this. And I've covered some of this before, already, I should say. So why do we want to model these processes mechanistically? It's because if we have that mechanism built in to mimic the biology and the ecology, the hope is it will give us a better understanding of how the disease is actually spreading, right? Or how it can spread. And like I said before, often this is because we want to be able to better control them, right? So if we think about, say, a vaccination policy for a given disease, and this is not the case for COVID-19 yet, but it might be in several months' time. But there are questions that we need to think about, such as how many individuals do we need to vaccinate, right? Do we need to vaccinate the entire population? If the vaccination is extremely expensive, that can become an important question, because the resources you're using to vaccinate are resources that could be going somewhere else. But often it's not possible to vaccinate all the individuals in the population. You may not have enough vaccine, right? So knowing what sort of coverage you need to try and bring an epidemic under control is useful. Similarly, how good does the vaccine need to be? We know that vaccines are not 100% effective. How effective do we need them to be? And obviously that's tied to this, right? The individual level efficacy and how much coverage we can get. We also have questions such as, which individuals should we vaccinate? If we're not vaccinating everybody, are there subpopulations that we should think about vaccinating? If it's children who are driving whatever the epidemic is, maybe they're the ones we vaccinate first. Or if there are certain subgroups who are really at risk from serious symptoms with the disease, which is the case with COVID-19 and influenza, maybe we should vaccinate those, right? And then the final one is, generally you think about this more in terms of livestock diseases, but can we vaccinate reactively, right? So if you've got some known disease suddenly comes into your country, starts infecting, can you set up a fire break to stop that disease getting through the entire population? Okay. Similarly, well, with COVID-19, another way that we think about controlling the disease is through social distancing, right? So questions there, how good does it have to be, right? A government can impose a lockdown, but we know that it's not going to be 100% followed, right? So how stringent does that lockdown that the government has to impose, knowing that not everybody's going to adhere to it, how good does it have to be to bring this under control? Are there particular subpopulations who should isolate? How long do we need this to do this for? And how and when do we stop? Do we just switch off, or do we relax certain aspects first, okay, or earlier than others? And the reason, and then the hope is that if we've got some model that we've fitted, calibrated to data in some way, hopefully a statistically rigorous way, but not always. But if we've got a model that we have confidence in, we can use that model to try and answer these questions, right? What should we do with our social distancing policy? What should we do with our vaccination policy? Okay, those answers won't be definitive, and they may need to be revisited over time as you get more information. But they're often, or they should be better than a back of the envelope policy prescription, right? That a policy dreams up. Okay.
Rob,
yes.
before you move forward to there's a question at the Q&A. Can you elaborate on the ways in which mechanistic methods may provide better understanding spread and control methods versus the disease surveillance methods?
Well, like I say, it depends what you want to do. So the mechanistic model is trying to get like I say, the actual number of cases that you see in a population, that actually occur in a population over time. And like I said, they're designed to do that, right? And we'll come on to what the models look like, but their output naturally follows the sorts of epidemic curves we see. The disease surveillance methods will do as good a job if, for example, we've got very high reporting rates, right? So if we actually see most of those disease cases, I'm not sure the mechanistic model gives you very much there. I'm not sure, is that answering the question? If the question is more about how does the model actually work, then we will come on to that. Of course, I have no idea whether you think that answered the question or not, because.
Yeah.
So I'm going to just assume.
Yes, and thank you. You answered the question, and thank you.
Okay. Yeah. Okay. Okay, so just quickly here, so other questions that we might be interested in, and this is more if we really have calibrated our model to data in some way, then we can also go on to ask questions that we tend to ask more as statisticians, which is, what are some important risk factors, right? Why are we seeing some individuals infected, some not? What subpopulations are most at risk, right? So this is more tied to that idea of using these models to do data analysis. And like I say, second half of the second section, I will talk more about that. But generally, we're using them to make forecasts. All right. So just before we actually put up the first model, I'll just talk briefly about some of the different types. So, and these are in increasing complexity, realism. I've put them in those orders. So we start with the simplest. So what you might term homogeneous models, and these are the first models that we're going to look at today. The basic underlying assumption in those models is that any infectious individual has an equal chance at any given time of infecting any susceptible individual, right? So we're assuming there are no individual level covariates that affect my chances of getting the disease or passing it on. So age, past vaccination, past infection history, all of that is being ignored. I'm assuming everybody's the same, but I'm also assuming that everybody's mixing homogeneously as well, right? They may be mixing at a very low rate, but anybody in the population I have an equal chance or equal rate of coming into contact with. We can then impose some structure on those sorts of models. And like I say, this is what I'm going to start off. So when people talk about things like the SIR and SEIR model, this is really what they're talking about. On top of that, you can start to impose some structure. Okay, so we can think about stratifying our population. We may stratify by age or by sex or by vaccination status. And generally what's happening in those models is that we have this homogeneity assumption within stratas. So we've got homogeneous mixing within the strata and homogeneous mixing between the strata, but those rates are different, right? So the rate of infection within a given strata is not necessarily the same as the rate of infection between stratas, okay? And these sorts of models I will also discuss this morning to some degree as well. If you take that a bit further, eventually you should keep stratifying your population, and you do it enough, you get to what you might term individual level or individual based models. Okay, and for those models, the chance of any particular infectious individual infecting any particular susceptible individual are going to depend on some individual level covariates. Okay, so these could be space, how far away are we? They could be connectivity through a network, right? Am I directly related to someone through this network, which could represent, you know, your domestic abode? Do you live in the same house? Do you live in the same region? Are you friends with someone? Is someone a sexual partner, right? So those sorts of things. And then all those other sort of individual level things like age, genetics, vaccination status. We can throw all of those into these sorts of models as well, right? And these are the sorts of models that I have worked on most of my career. Like I say, in a way, they're mathematically less interesting in that most results are not analytically tractable, but they're more realistic. Okay, the downside is they're computationally quite cumbersome. And then I don't know where you put the divide between an individual level model and an agent-based model. I tend to think about an agent-based model as a very high dimensional, high complexity ILM, okay, individual level model, right? So when you really you may have, these sorts of agent-based models may have dozens, hundreds of parameters representing all sorts of things that the population are doing. So they can be extremely realistic, but they're very hard to parameterize in a realistic way, right? Or at least you have to base it on some pretty strong assumptions. Okay, so these are the sort of the four types that I've sort of got in my head. And like I say, the focus of today will really be on those two types. But hopefully, if I don't go too slow, I'll have a chance to talk a little bit about these as well. All right, so let's start. I'm going to start simple. We've got the homogeneous model. So what characteristic does this model need to have? So two characteristics which are really tied. One is the effect of time. Okay, we know that the number of infections are going to change over time, and the incidence rate, the number of new cases, is going to change over time because it depends on how many individuals are infected at any time, right? And that's why we tend to get those sort of epidemic curve shapes. If we're not controlling the disease, this occurs, the inflection occurs there because essentially you're running out of susceptibles, right? There are fewer people to infect, so the number of cases goes down. Similarly, from a statistical point of view, we know that the infection events are going to be non-independent of each other, right? So like I say, these things are tied. If I was doing a survival analysis on, say, cancer data, my rate or risk of getting cancer at any time probably doesn't depend on anybody else's after we've allowed for various risk factors. However, my risk of getting influenza does depend on how many people in my neighborhood or at my place of work have influenza, right? So the non-independence of the infection events does invalidate a lot of the sort of off-the-shelf statistical models that we tend to use, which is another reason we go back to this sort of mechanistic approach. Okay, so I think I've said all of that. Yeah, and then just one last thing before we actually look at a model. Is that right? Yeah, that's right. One last thing. There is a choice here of modeling in discrete time or continuous time. So most of these models, when if you look at the models for COVID-19, they're continuous time, right? When people talk about an SIR model, they're talking about a continuous time model that generates the exact time of infection for individuals, right? But you can model in discrete time. And actually a lot of the modeling that I've done is in discrete time, but it's still mechanistic, right? The mechanism is still, or the mechanisms are still built into the model. But you end up producing data that's more like time series data, right? Counts or lists of individuals infected every day, for example. In this talk, I'm going to stick with continuous time almost the whole way through, okay? There are some advantages to working in discrete time, but some disadvantages as well, which hopefully I'll have time to talk about later on. Okay, does anybody have any questions there?
Okay, Rob, there is one question coming in. Let me, okay. What if you control for non-independence through covariates in individual level models, e.g. a survival models? And then we have another one coming.
Well, the survival models, you can obviously control for individual level covariates, but there's an underlying assumption in your survival analysis model that the hazard rates are independent, right? The rate at which events occurred are independent. And that is not true in an infectious disease, okay? But my rate of infectivity is going to depend on who else is infectious in the population. I mean, if you try to put that in as a covariate, you basically come back to a discrete, a continuous time disease model of some sort, right? So you can do it that way. But then all the nice computational tricks or mathematical tricks we use to do things like, you know, allow for censoring suddenly become much harder to deal with, which is usually gives you a computational problem.
Okay, so some additional questions. One is the vaccine was mentioned to control infection during spread, but does the model also consider other public health measures during pandemic? Can do,
and I'll show you an example later where the first thing that we did when we started modeling COVID-19, and I say we, this was really driven by my PhD student, Mark Lowerson. I have to say that because he's probably listening. The first thing that we did, or he did, was try to incorporate contact structure in the population, right? So that then you could try to mimic the idea of social distancing policy. But we'll come on to that later on.
Okay, so two more questions related to the discrete and continuous time approach. One is, what is the specific rationale for choosing between these two approaches? The other is, what is the unit of time in continuous time model in seconds?
Okay, I'll answer the second one first because it's easier. The unit of time is whatever's most convenient for you. So, you know, if you're modeling HIV, then months probably make sense for your unit of time. If you're modeling a common cold, then days is probably a more sensible choice. And then the rationale for choosing between discrete and continuous time. So the primary reason that I would go for a continuous time model in some situations comes, well, we are going to talk about this later on, but we have an inherent problem in disease modeling, which is that we don't observe a lot of things that we want to observe. For example, the infection time, right? So I never observe the infection time. I may observe a reporting time and know that the infection occurred before, but I don't know when it occurred, okay? However, in some diseases, you may be able to get that down to a level where you can identify someone got the disease on a particular day or week from their symptoms, right? So in discrete time, your time points are representing an interval of continuous time. So it may be easier to map your data points, right, to those intervals. If someone comes into a doctor's office with a certain rash, you know, oh, this is whatever disease it is, and that must have occurred within the last week, for example. If you've got that sort of situation, you can use your discrete time model, and then you don't have to worry about the fact that you can't estimate the individual infection times, which we'll talk about later on. And same for things like infectious periods.
Okay, great, Rob. No more questions at this point. Thank you.
All right. So the SIR compartmental model, which I would say is the classic infectious disease model. So whenever I need to look up something on these models, the book I tend to go for is the Keeling and Rohani book. That's partly because I worked with Matt Keeling in the past, but partly because I think it's a really nice book. So all of what comes over the next few slides really has come from that book. Okay. So some assumptions that we're making with this model. So first off, we're assuming a closed population. Okay, so I'm assuming there are no deaths, there are no births, there's no migration. Right? So if in actuality I have births and deaths, but they're at a low level, that's probably reasonable. The migration issue is more of a problem most of the time, right? But we can extend those models to allow for, or these models to allow for that sort of thing. But in its basic form, I'm assuming no births, no deaths, and no migration. Okay. Time is considered continuous, okay, and there's the answer to that question. Unit of time is whatever's most suitable, right, or whatever's most convenient in terms of our disease. As I said before, with these sort of simple models, we're assuming that individuals are homogeneous with respect to the disease, okay? And we're also assuming that they're mixing in the population homogeneously. And the other thing that we're assuming is that individuals become infectious as soon as they're infected with the disease. Okay, so we don't have what we call a latent period. Now, in reality, that's not true. When you get a disease, there's almost always a certain period of time before you start shedding the virus or the bacteria, whatever it is, and infecting other people. But in situations where the latent period is relatively short, it's reasonable to ignore it. And even when it's a little bit longer, it often just becomes an issue with the scaling of the parameters. So you can still work with these models. And also it's easy, as we will see in a minute, to introduce that latent period if we want to. But I'll start with this simple model. So the SIR compartmental model, so in disease modeling, we talk about compartments, but it's basically a multi-state model, right? So I could talk about states rather than compartments. And the basic idea is that at any given time point T, each individual in the population can be in one and only one of three states or compartments. Okay? So they're either susceptible to the disease, which means they don't have the disease yet, but they can contract it. Okay, so they're not immune, right? They have the ability to get the disease. Ability is not the right word, but anyway. Or they're infectious, right? So they've contracted the disease and then they can immediately pass the disease on to others, to other susceptibles. And then later on, they enter the removed state, the R state. Sometimes we use R to mean recovery, which is sort of the nice outcome from a disease where you recover and then you develop immunity. But of course, more generally, the removed could mean you've died from the disease, or it could mean that you've isolated, right? Or been isolated. You may have been put into quarantine, self-quarantine. If we're talking about a livestock disease, then that farm may have been shut down, so no animals are coming on, no animals are going off, that sort of thing. Okay, but in some way, what this removed means is that you can't interact with the infectious or the susceptible population anymore. Okay. So a little bit of notation. So ST is going to be the proportion of susceptible individuals in the population at time T. IT is going to be the proportion of infectious individuals in the population at time T. And RT is going to be the proportion of removed individuals in the population at time T. Okay, and I'm going to emphasize that I'm talking about proportions here. Sometimes we won't talk about proportions, we will talk about numbers, counts, but at the moment it's going to be the proportion. So S, I, and R are going to add up to 1 at any given point in time, okay, because this is a closed population. And then the model looks like this. Okay, we have a set of 3 equations forming an ordinary differential equation system. So basically determining the rate of change in those 3 compartments. Okay, so the first one up here is the rate of change of S. Okay, so the proportion of susceptibles are changing with a rate given by minus beta, which is our transmission rate parameter, times the number of susceptibles, the proportion of susceptibles and the proportion of infectious individuals, okay? So few things going on here. We can see that obviously the rate of susceptibles is going to go down. And what's happening to those susceptibles? Well, they are entering the infectious state. So the rate of change of the infectious part, so start that again. The rate of change of the infectious compartment is going up by beta times S times I, and I'll come on to this bit in a minute. Couple of points here. You can see that this term here that I've highlighted is what we might term the incidence rate. Okay, it's an incident rate in continuous time, but it's basically giving us it's standardized by the number of the population. It's basically giving us the number of new infections at any given time point, right? Or we can get the number by multiplying by n. The beta itself, oh no, let's come on to that later. So that's the rate of change of the susceptibles. Those individuals are moving to the infectious compartment. And then some of those individuals who are infectious are recovering, right? And that's what this the second component there is doing. We have a removal rate, gamma there, which is describing the rate at which infectious individuals become removed. And so they are going into the removed state with the rate gamma IT plus gamma IT. Okay. couple of things to point out here. So these are rate parameters, right? So for example, 1 over gamma here is going to give me the infectious period for individuals. If we're in a stochastic setting, it would be the average infectious period, okay? Because the infectious period determines how long you're infectious for, and after that, that's when you enter the removed state. The other thing I want to say is that this beta is a product, like I say, of both the biology and, or let's say the disease and the population. Okay, or I shouldn't say product, it's a function of, right? It's describing both how intrinsically transmissible the disease is, but it's also capturing how the population is mixing, right? And you can derive these equations by thinking about the contact rate in the population and the actual, probability of a contact occurring between two individuals that mix, right? Okay, but that's our basic model.
So Robert,
yep.
There is a question now. Do the rates include the case where a susceptible person becomes removed, e.g. via isolation, instead of becoming infected?
So in this, not directly, no. So we will have to extend this model in order to allow for that. What you do have to think about is what that infectious period means, right? So if somebody gets a disease and they're infectious for 10 days, you might think, right, so I set the removal rate such that the infectious period is 10 days. However, if that person, when they develop symptoms, the symptoms are so severe, they're going home and never meeting anybody, you might want to think about an infectious period that's shorter, right, for those individuals. So you can choose to incorporate that sort of ecological information as well as the biological information. But there are different ways of doing that as well, okay? But we can set it up so that some proportion of the population move from that state to that state. Okay, and I'll talk a little bit about that in a little while.
Great, Rob. There's okay. No more questions. Thank you.
Okay. Okay, so quite often we represent these things as a flow diagram, and when these results from these analyses get published in medical journals, they don't really like to see differential equations. So you'll more likely see it in terms of a flow diagram, which is very simple for this model. So the way I've drawn it here, that's describing the rate at which individuals are moving from state to state across the whole population. You'll quite often see it done on an individual basis. So you might have beta I, T, and just gamma there. So that would represent the rate that individuals move through these compartments. This would represent the rates that the population moves through these compartments, okay? All right, and we'll come back to these flow diagrams a bit later on. Now, if you want to solve this equation, or deterministically simulate from this series of equations in R, it's very easy to do. You can do it with the package DESolve, differential equation solver. I won't spend a lot of time on this because I think it's all pretty straightforward, and I assume most of you are familiar with R. You basically, you install your package and give R access to the library, then set up a function here called SIR, which you can see essentially contains the differential equations that we had 2 slides back, okay? So that sets everything up. The next thing I need to do is initialize this. So what's happening at time 0? And what I've done here is I've said that 0.999 of the population is in the susceptible state. So if my population is 1,000 individuals, 999 of them are susceptible. I've got 0.001 of my population infectious, and nobody's recovered, right? And I can set those initial conditions to whatever I like. I've set the parameters here. So my transmission rate, the beta I've set equal to 1. Oops. The gamma is the recovery rate, or the infectious, well, let's call it recovery rate. The removal rate. The removal rate gamma is set equal to 0.2. And then what I'm doing here is I'm setting a bunch of times at which I want to observe this process, right? This is a continuous time process. So I'm going to ask it to observe at times 0 up to 40 in unit steps. Okay.
So, Rob, while you're at the gamma, there is a question about the gamma. Gamma is the rate of recover and the death both?
Yes. In this model, it's any way in which individuals are moving into the removed state. So that would be a composite of deaths and quarantine and recovery and all those sorts of things. Okay. If you want to make it more complicated, which you can do quite easily, we can do that, and I'll talk a bit about that in a little while. But at the moment, it's any movement from infectious to removed.
Okay, and there's there's a couple more questions. Presumably, the flow of the individuals from S to I to R is one way. Is this included mathematically somehow, or is it unnecessary to do so?
It is included mathematically. So if we go back to our differential equations, you'll see that in the first line there, the rate of change for the susceptibles is negative. So it's always going down until it gets to 0. Okay, in this model, there's no way to get back from removed or infectious to susceptible. But once again, we can change. This is just the sort of vanilla infectious disease model that we go for. We can change that if we want to, and often we would.
Okay, and then there's one last question for the moment. How do we choose the most appropriate parameterization?
Parameter, do you mean the most appropriate model, or you mean the actual settings of the parameters? And if we're talking about the settings of the parameters, I'll come on to that. Okay. If we're talking about the model, then obviously this is a mechanistic model, right? So you think about the disease system, you think about what could be going on here, right? What does an individual that gets infected become immediately infectious? Do you have asymptomatic cases you want to account for? Can removed individuals become susceptible again later on? Okay, so you can build your model structure, and people do them. You build very complicated model structures. Of course, if you do that, you then have to find a way to parameterize it, which I'll come back to.
Okay, so yeah, the question being clarified is about the parameterization is about the initialization of the parameter value, and then follow up by another related question: what does 0.2 gamma mean exactly in English, in text?
In English, so it basically means that the infectious period is 1 over 0.2 is how I would think about it. Right, but it's the rate of recovery, right? So it's an instantaneous rate of recovery. The probability of recovery in a very small time interval for any individual. Okay.
Okay, great. No more questions.
It's probably easiest, or what I generally do is I transform it back to thinking about the infectious period, which is the period at which individuals are infectious for. Okay. Okay. Sorry, didn't quite finish, did I? So to solve the ODE there's an ODE command. Okay, so it actually chooses from by default, it will choose from a variety of methods for solving the ODE, depending on the stability or the stiffness of the ODE. And then finally, I've just got some commands there to plot the output, which looks like this. Okay, so we can see now the output or the solution to this ODE system. We got 3 curves going on here. The one that we normally think about, and the one that I plotted sort of for the foot and mouth disease at the beginning, is this curve here, which is essentially the number infected. I should really say infectious, shouldn't it? But I didn't spot that until now. Well, infected and infectious mean the same thing in this model, so perhaps that's fine. But that's showing you the number of infectious individuals over time. We can see that we get a peak just past about 10 time units, whatever that represents, and then the curve tails off until I think by about time 40, pretty much, well, depends on the number in your population, right? Because this is a continuous response that we're getting, but pretty much the proportion of susceptibles has gone to 0 by about time 40 here. And at the same time, you can see the depletion of the susceptibles. So we start off with 100% or almost 100% susceptible, and then that tails off to 0 as well. And then the number who entered the recovered, I've written recovered, should really say removed, because that could be various mechanisms, right? The removed state over time as well. Okay, and I'll clear this because I think I've just destroyed all the colors. That's basically what's going on. And this is a deterministic system. So if I run that again, I will get exactly the same output. Okay, describing how the disease would pass through our population under this model. Okay.
So Rob, there is a question. Could you explain a bit intuitively why the incident rate is a production of a negative beta S and I?
Oh yes, I meant to do that and I forgot. Sorry, thank you for that question. So if we go back to the equations, so if you think about it, it is describing the number, or in this case, the proportion of individuals moving from susceptible to infectious. Right? So it makes sense that more individuals are capable of doing that if we have more susceptibles. Right? So we multiply the beta by the number, the proportion of susceptibles, so that more of them, the more there are there, the more that more can move. Right? At the same time, you're more, as an individual, you're more likely to be moving into the infectious state the more infectious individuals there are in the population. So we also multiply it by the IT as well. Okay, so the more susceptibles we have, the more infectious individuals we have. Overall, the more individuals can move from the susceptible to the infectious state. And of course, this is why we get that tailing off, because as this ST here goes down, as the number of susceptibles are used up, that incidence rate will go down because there are fewer to infect.
Great, okay. Thank you. Yeah, no more questions at this point.
Okay. All right. So I'm going to take a little bit of a tangent here and just talk about a couple of metrics, which I'm sure if you weren't familiar before this epidemic or pandemic occurred, you're familiar with now. So one is called the basic reproduction number, or R0, right? So the basic reproduction number, or reproductive rate, it's often called. What is this? This is the expected number of infections that result directly from a single infection in an otherwise wholly susceptible population. Okay, so this is really, and the 0 here is referring to time 0. This is what happens when, or sorry, the number of infections that result directly from the very first infection in the population. Okay. it's going to be deterministic in a deterministic model. If we've got a stochastic model, then what we'll often do is take an average, especially if it's an individual level model, because then, you know, where an individual is in space, for example, is going to determine partly how many individuals they infect. So you might take a Monte Carlo estimate averaging over lots of simulated infections. But in the SIR model, the R0 is very simple. It's an analytic and has closed form solution. So we get it by just taking the beta, the transmission rate, and dividing through by the recovery rate. Okay, so or multiplying by the infectious period. Okay, if you want to think of it that way, which is in some ways more intuitive. Right? So the direct number of infections from that single infection, not any of the secondary ones, right? So not the ones that follow. So that's obviously going to be high, the higher the transmission rate is, but it's also going to be higher the longer that initial infection is infectious for. Okay, so that's why we divide through by the recovery rate or multiply by the infectious period. Now, it's this quantity, the R0, is interesting or of interest primarily because it has this threshold, the epidemic has a behavior that relates to the threshold or differentiating behavior that results from the threshold R0 equals 1. Okay. That was a very garbled sentence, wasn't it? So basically, it boils down to this. If R0 is greater than 1 for your SIR model, your epidemic's going to take off and everybody in the population will be infected. If R0 is less than 1, your epidemic's going to die out. Okay, if it's equal to 1, it will just be a straight line. But you know, if your model is not deterministic, if it's stochastic, then rather than saying if R0 is greater than 1, the epidemic will take off, we'd say that it tends to take off. Right? It can die out, but it's more likely to take off, and the larger R0 is, the more likely that's to happen. But in the simple deterministic model, the epidemic behaves deterministically from according to that threshold. So it's a metric that's useful for describing the disease system. It's also simple, and the epidemic behavior in relation to that threshold is also simple as well. So that's why it's a very popular threshold. And I'll just show you sort of what the curves. We change that R0 by changing these parameter values. So if I set my beta to 1 and my recovery rate to 0.2, so my R0 is 5 now. Well, that's what I simulated before. Okay, that's the curve that we saw previously. If I then change this, so I halve my transmission rate, so go from 1 to 0.5, but I keep my recovery rate the same. So R0 has now halved to 2.5. You see that we get a much slower epidemic curve taking off like so. Okay. If I go further, and well, actually I've kept beta the same here, so set that equal to 0.5, but double my recovery rate. So I'm halving the infectious period. So R0 is halved again. Is it halved again? Yep, halved again, down to 1.25. You can see now, well, actually, it's very hard to see what's going on with my epidemic curve at all, but it is taking off very slowly. And if I ran that for long enough, I would get a curve with this shape, but it would be a very flat, long curve.
Rob, yeah, there are 3 questions coming in. One is the R0 is based on certain time unit, right? And then the 2 other questions are related to the big N. Does the big N matter?
In this model, no. So this is a frequency dependent model. what's called a mass action, right? It's just the proportion of individuals infectious in the population that's driving everything. If you changed it so that the SI and R weren't the proportions, but they were the numbers, then yes, it would, and you would have to rescale the R naught. Okay, so this changes. Okay, it needs to be rescaled. Okay, it's actually rescaled by the number of susceptibles, I believe, which is obviously related to the big N.
And then the first question was the R naught is kind of have a time unit.
Time, well, it does in a sense, yeah. I mean, it's based on a dynamic system, right, which has time units. So if you change the time unit, oh no, it won't. No, it's going to be the number of secondary infections. So no, time doesn't come into it. I mean, so okay, let me go back to that. If I rescale time, so I change my time unit, to get the same output, I would need to rescale my transmission rate. Okay. So, but the R naught would end up the same.
Okay. And then, yeah. And then there's another follow-up question. In mathematical terms, is it correct to say if S subscript T greater than 0, if and only if R greater than 1?
ST, meaning any time point? No.
Oh no, that was a limit. Sorry, not greater. Sorry. yeah. So as subscript T goes to 0.
Yeah. If R naught is greater than 1.
If and only if R greater than 1.
Yeah, in the deterministic, no. If it's greater than or equal. Okay, so if you set it equal to 1, everybody will get infected, but you will have a flat infection curve until everyone's infected. But otherwise, yes.
Okay.
Okay.
Thank you.
Okay. All right. And then just a couple more. So if I change my beta now, I'm changing both, aren't I? Yep. Set my beta to be 0.2 here, my gamma to equal 2.5. So now my R naught is 0.8. Remember, I'm just infecting 0.00, was it 0.001 of my population? Essentially, what happens is it dies out pretty much straight away. Okay. If I actually infect some more, so I infect 10% of my population rather than 0.1%, which is what I was doing before, you can see better what happens, right? So infections are still occurring, and more individuals are getting infected, and we see that in this curve here, but they're being depleted at too high a rate for it to be sustainable. So individuals are recovering too fast to keep the individuals, to keep the epidemic going. Okay, so that's one thing, the R naught. And actually, you may have noticed, well, I did anyway, that at the beginning of the pandemic on news reports, they were often talking about bringing down the R naught, right? And that was what we wanted to do, which would sometimes get me shouting at my radio because you can't bring down the R naught, right? The R naught is an intrinsic function of the disease and the population in its natural mixing state, right? It really only refers to this quite unnatural, in a way, scenario, which is that you've got one infection occur, well, I say it's not unnatural, but unobservable, I should say. You've got one infection occurring in the population, and you want to know how many they directly infect. Okay. Since then, they've stopped talking about bringing down the R naught, and they've talked about bringing down the R, or what we often call the RT, which is the effective reproduction number. Okay, and that's actually correct, right? So we don't really tend to observe the basic reproduction number in real life because when infection occurs in a population, we don't normally know until some time afterwards that it's actually occurred, right? It's really of mathematical interest because it has this nice predictive, well, it's simple to calculate, and it has a nice predictive relationship to what's going on with the epidemic. In terms of epidemiology, what we're often more interested in is the effective reproduction number or reproductive rate. And that's the expected number of infections to result directly from a single infection, a new single infection in the population at any given time t. Okay. Now this differs from the R0 in quite an important respect, in that it depends on how many susceptibles there are left, right? For the R0, the number of susceptibles is set in stone because you've only got one infected individual and everybody else is susceptible. This thing will change over time as there are fewer susceptibles to be infected, and it's given by RT equals R0 times the number of susceptibles. Okay? And it's really this that we're trying to bring down, right? It has that same threshold behavior, right? If we can bring it down below 1, then the epidemic under an SIR model will die out. If it's above 1, it's going to take off. Okay. And this is what we're trying to do in COVID-19 with our social distancing and maybe later on, hopefully, a vaccination policy. Okay. So that was just a little aside because this term or this metric comes up a lot in these sorts of studies. Does anybody have any questions they want to ask?
So there's one question coming with small big N. Is it good to use the stochastic model rather than the deterministic?
Well, I would say whatever the N is, it's good to use the stochastic model. Okay, we're starting with the deterministic. It's probably more important in a small N because there is, you know, there are probabilities that your epidemic could die out at any time, that the SIR doesn't allow for it, for example. And if you simulate from a stochastic model repeatedly, you will often see quite variable behavior, right? Plus, if we want to do any inference on this stuff, we have to move to the stochastic model anyway. So, I mean, personally, I tend to prefer using the stochastic model. It does increase the complexity to some degree. And certainly the computation will be increased. If you're running a big simulation study and you have to do replicates over lots of realizations for the same parameter values, for example.
So there's another double checking question. Things like social distancing and the vaccine policy change the value of beta and gamma in the DEs, right?
If you're using an SIR model like this, yes. But it's difficult to measure how they do that. And actually we're going to look at an extension in not the next section, the section after, where we try to mechanistically allow for contact structure in the population. Okay, if I know that, you know, we've shut down schools and 50% of people aren't going to work, and I've got an SIR model, that's really not obvious what you do with beta to allow for that, right? So we want to reformulate this model or extend this model to allow for that.
Mm-hmm. There's another question coming in, needs some clarification on the notation. So the R subscript T in the previous slides means the means the proportion removed, but the RT here means the effective reproductive number. It's a little bit confusing.
Oh yeah, that is confusing, isn't it?
Okay.
I apologize for that. So originally my SIR were STIT, RT to represent the proportions. And then I decided that was ugly. So I put in the subscript, forgetting that this is the same. So yes, apologies for that. You're right. They're the same thing. This is not the same R. as the proportion.
Okay, so one more question. So it is regarding the RT, the effective reproduction number. Is it fair to say the RT is the same as R0 calculated at time t rather than at time 0 with different number of susceptibles, of course?
Yes. Okay. So basically R0 is a special case of RT.
Mm-hmm. Okay. There's one more question, sorry, yeah. Can RT still be interpreted as the ratio of beta and the gamma after time 0?
It needs to be adjusted. So RT is going to be this, right? So it's the R0 is still there, so that's beta divided by gamma, but the ST is also needed because the number that you can directly affect at any given time is going to depend on how many susceptibles are left in the population. Does that make sense? I'll assume that makes sense.
Yeah.
Okay.
Yeah. No objection. Okay. Yeah, thank you.
All right. Okay. So what I'm going to do now is, in this next section, I'm going to go through a few extensions. I'm going to try and go through this reasonably quickly because I feel like I'm a little bit behind now. Or at least I'll go through some of this reasonably quickly. And some of it I have touched on before. So one thing that we might want to think of is what I mentioned at the beginning, right? So our model where S, I, and RT are the proportions of the population, this is known as a frequency dependent or mass action model. I prefer frequency dependent because it sort of makes more intuitive sense. But basically it's saying that the transmission dynamics in the population depend on the proportion infected, or the frequency of infections, but they don't depend on the population size, right? So I'd get the same curve whether my N is 100 or 10,000. Okay. Now the alternative, and it's an approach that actually I use most of the time when I'm doing individual level models, is to use a density dependent model where SI and R are the numbers of the population within each respective state. And we will actually transfer to that in the second section. Okay, so the difference here is that the transmission dynamics are going to change depending on N, right? And it's called a density dependent model because you're basically assuming the population resides in a fixed area. Okay, so if N goes up, the population density is going up as well. So that's where that name comes from. In the SIR model that we've just seen here, it really doesn't make any difference, right? It's just an issue of scaling. You either multiply your beta by N or divide your beta by N, and you get back to exactly the same model. It does become important if you start having births, deaths, migrations, that sort of thing that can really affect the population size. Okay, so you might want to give some thought to whether a frequency dependent or a density dependent model makes more sense. The other thing that I want to talk about, and I'll go into a little bit more depth in the next slide here, is that the SIR is sort of the go-to framework, but there are lots of different compartmental frameworks. In fact, essentially your imagination is the limit here, right? Although you'll eventually reach a point where it's completely unrealistic. But so one thing, we can actually simplify things. So sometimes people will use an SI model where they assume that individuals are infectious forever. Okay, and that makes sense sometimes if you're just doing a modeling over a short period of time and your infectious period is relatively long compared to your observation period. Or diseases like HIV, so not so much now because we have treatments, but it used to be that you're infected with HIV, you're infectious for the rest of your life, right? So there a removal rate, a removal stage would represent death maybe, but quite often you wouldn't include it at all. You could just have an SI model. Another very common thing that we would do is use an SEIR model. Okay, so the E there stands for exposed, and that refers to your time in the exposed period, or sorry, time in the exposed state is akin to your latent period. So we assume there's some time when you get the disease that you have it, but you're not yet infectious. And then after some time, your latent period, you enter your infectious period, and that's when you can start infecting individuals. And I'll talk a little bit more about this one, just to show you how the model changes if we introduce that compartment. And then other things that we can do is we might choose an SIS or an SIRS, right? So in these two frameworks, or an SEIRS, we assume that people recover, they may, or maybe go into quarantine, but more generally they recover, they have immunity, but after some time that immunity wears off and they go back into the susceptible state. So you might use models like this for, say, influenza over a long period of time, where you know people get immunity from a given strain, but that immunity wears off. And also, of course, next season a different strain comes in, and that immunity doesn't protect you, right? But so we can allow the compartmental framework to lead us back to the susceptible compartment. And which one we choose is probably going to depend on the disease we're studying. And, you know, sometimes we make a choice about the model depending on the data, right? So we may believe there's a latent period, but have no idea what it is from our data. So, well, maybe we can try and estimate it, but sometimes we may make simplifications based on the quality of the data. Okay, any questions there?
At this moment, no, thank you.
Okay, so just quickly, I'll show you what the SEIR model looks like. Okay, so we had three equations before in our ODE system. We've now extended this to 4 because we've got 4 compartments or 4 states. You'll note that the rate of change for the susceptible state here is the same as before. Okay, it depends on the number who are susceptible at any time, or proportion susceptible at any time, and the proportion who are infectious. But now those individuals who get infected move into the exposed state where they're not yet infected. And then they enter into, that should be just below, but it's been shifted over. They enter into the infectious state at a rate given by this parameter sigma, okay, which depends also on the proportion of individuals in the exposed state. And then we're back to where we were before, right? So then the infectious individuals are being entering the removed state at a rate determined by, on the individual level, determined by gamma. At the population level, that rate of transition is gamma times I. Okay, so it's very simple to expand these things. I've obviously just put in one more compartment here, but if I start putting in multiple compartments, you can sort of see how that's going to work out. And obviously it's very easy to take this and adapt the R code that we had earlier to solve this set of equations, or produce output from this set of equations. Okay.
So Robert, there is a question coming on the modeling.
Yeah.
How transmission dynamics in frequency dependent model don't depend on population size if the states models are proportions of the population? Can you explain a little bit more?
So they're not, well, N doesn't come into it, right? So the size of that population isn't a component of the model up here. It's just the proportion. Okay, so there's if I run this the same model, assuming the same proportion of my population are infected, but the population has doubled in size, it doesn't change anything, right? However, with the density dependent model, the incidence rate, if this ST and IT are now integers, or well, actually they'd be real numbers in the ODE system, but if there are the numbers of people, then the more there are in the population, the larger those things will be. Okay, does that make sense? Like I say, it doesn't really make much difference because I can get back to the other model by rescaling this. Right? If I divide my beta through by n, then I've got back to where I was before. But if I start allowing for demographics, for migration, for births and deaths, then the rates that control those births and deaths will affect the numbers in those compartments, and that will actually affect the disease dynamics themselves.
There's another question. Is there a way to incorporate a clustering such as households and families in the SIR model?
Yes. Well, I'm going to talk a little bit about this in a minute. Yeah, there is. In fact, the model that we use for COVID-19 does this sort of implicitly. But yes, you can. I mean, I'll admit that if we start thinking about whether people are in the same household or not, then I think at some point you make these models complex enough that you'd consider them individual level models almost, right? But so yes, we can incorporate it. What you call that model at the end, I don't know. Does that make sense? It might make more sense when I get to that section.
Yeah. So we can only use we can only use density dependent model when incorporating population dynamics, but not the frequency dependent model.
No, you can use it in any situation. I mean, if you want to model, if you want to go back to my R code and change the SIRs to the numbers rather than the proportions, it will run, and if you scale beta, you'll get exactly the same looking curve output, right? Except, you know, on the Y now there's the numbers rather than the proportions. So you can use the density dependent model. What I'm saying is that if there are no, if you've got a closed population and n doesn't change, it doesn't really make much difference. It makes difference in terms of, you know, how you calculate R0 and things like that. But basically it's the same model if the population is closed.
It's one last more like comment would maybe a practical demo in R would help.
It may do, but I was originally going to do that, but I just found that there's too much material. I mean, honestly, if you take that slide with the R code and run that, it's very easy to change that. I mean, if you really want a practical demo, then I could set up another, you know, workshop or something in the future, but I really don't have time to do it today.
Okay. So do you have time for 2 more questions right now? So
you want an honest answer? No, go on.
So first of all, quick question. How is reporting date and infection date differences / bias was considered in the SIR model?
We'll come on to that this afternoon.
Okay. Is any relationship of the 4 functions S, E, I, R besides the differential equations? If there is any interpretation of this?
Any interpretation of what?
I don't. Yeah, the question. I guess there's a typo. Is any relation? Is any relationship of the 4 functions S, E, I, R besides the differential equations?
No, I don't think so.
Okay.
If I've understood the question right. Mm-hmm. I mean, the differential equations define the transition rates, right, between the compartments. So for this modeling framework, that's all there is, right? But you can make the framework more complicated.
Okay, great, thank you. Yeah, so if the Yi Zhao who asked question, if it's not clear, just type in the Q&A. We can answer that later. Thank you.
Okay.
Yeah.
Sounds good. All right. So, okay, so I won't spend too long on this, but I mean, I've talked about how you can make these things more complicated, and just rather than write out the equations to save time, if I just think about like a flow diagram, so I could have a situation where susceptibles, I know that some individuals are going to be infectious, but say asymptomatic. Okay, so they're not showing any symptoms, and some of those individuals will then go on to be symptomatic. Okay, there should be T's on here as well, right? But I also know that some individuals will go directly from susceptible to symptomatic. Okay, so I can think about a structure like that instead of simply going from S to I. If I want to think about, well, some of these symptomatic cases are going to recover, so I could turn my R to a real recovery and a death state. Okay, and then I can have parameters associated with each of those edges between the boxes, which would determine the way that individuals flow through the population. So there are all sorts of things you can do. I can also, if I want, I can think about an inflow into the susceptible population representing migration or births or deaths. Okay, so there'd be another parameter associated with that. At the same time, I may have individuals coming in from the population who are already infectious. So they're going directly into those two states as well. Okay, so I can build up just through the flow diagram much more complicated structures than just the SIR. Okay, so allowing for more compartments. But then I have to think about the relationships. Like what's going to, I mean, for S going to I, it's going to be, you know, a parameter for asymptomatic and times ST, IT. Well, actually, it's got two lots of ITs now, right? So I've got the I asymptomatic plus the I symptomatic. Okay, and then there's a question of do I make those the same, etc. So this can become quite complicated, and you have to think about what you're doing. But conceptually, it's quite possible to come up with these complicated models and then turn them into the differential equations if you want to run them. Okay, so I've gone through that quite quickly. I am going to go for an example, which is sort of a similar idea, and that's accounting for subpopulations. Okay, and I'll go through this a little bit more slowly. So I mentioned before that that type 2 model, the structured homogeneous model, we may want to include some population structure for representing differences between the sexes, between age categories, between races, between locations. So I could enter sort of, I can make introduce a spatial component to this. If I think about two cities and how they relate to each other, or maybe in the case of Calgary, we could think about the population of Calgary and the population of Calgary that work at Cargill, right? The meat processing plant where we had 50% of the workforce infected. Okay, so I can structure the population in various ways. And when we do this, we generally call it a meta-population model. Okay, so we've got these subpopulations and they're interacting, right? They're basically extension, or we can write them in different forms actually, but I can extend my ordinary differential equation type models to allow for this. And what you're basically saying is that each subpopulation has an SIR model that's generating its infection, but then there's also some interaction between those subpopulations defined with different parameters. Okay, so a very quick example, if I wanted to have a sex stratified metapopulation model, I might break my population into two components. Okay, so I've got the females and males, and each of those individuals can be either in the susceptible, the infectious state, or the R state, right? So I now got, oops, get my pen back. ST, IT, RT, F for females, and ST, IT, and RT for my males. Okay, and then I can think about how I would want to parameterize this model, right? And these, once again, these could represent the proportions of the whole population, or they could represent the numbers, depending on how you want to do it. So if we think about the first thing, so let's think about females getting infected. Well, obviously females can be infected by other females. So I have a transmission rate there, which I've called beta FF, meaning infection from females to females. And that depends on the number or the proportion of susceptible females and also infectious females, okay, because they're the ones infecting. At the same time, obviously, females and males do not live in separate populations, we interact. So I'm going to allow for males to infect females. So I have another parameter, which I can allow to be different, right? So beta MF, that's male infection to female, or male to female infection, I should say. And that depends on the number or the proportion of the females. But now it depends on the number or proportion of susceptible females, but it also depends now on the number or proportion of infectious males. Okay, so now I've set that up so that females can be differentially infected by either other females or males. We carry on, we can do the same thing for males, right? So I've introduced transmissibility parameters for male to male infection and female to male infection. And then we have to think about the recovery. So I could allow females to recover at a rate given by gamma F, and the males to recover according to a rate gamma M. And then there's going to be a question, do I actually want those things to be different? They may be the same, maybe it makes more sense to have them the same. This is obviously an estimation / calibration issue, okay? But I can break my population down into these different structures. And what I'm basically allowing here is for not movement through these compartments, but interaction between these compartments, like so. Okay. All right.
So Rob, there is a question regarding the implementation of this subpopulation analysis. Can we just implement these models in the DSolve package?
Yes. So if you try to implement this, this would now be 6 equations instead of 3 equations, right? And your incident rate would obviously be different. But yep, it's pretty straightforward to do. And so if you want to attempt to do this, I think you should be able to do it quite easily. If you get stuck, drop me an email and I can send you some information. Actually, the Keeling and Rahony textbook that I mentioned at the beginning, it has the differential equations for lots of these models, including this one, I'm pretty sure. And all the ones with the demographics. So if you go to that textbook, you can see the differential equations, and a lot of them have been coded up by other people. So if you then Google this stuff, you'll find code that will do most of it. Okay, but I'm more than happy to receive emails if people do want help. I tend to prefer to do this from first principles, right? So I think about it myself, code it up, and then maybe check it against someone else's Okay.
Yeah, no more questions. Thank you.
Okay, I need to.
Oh, just one. Sorry, one more coming in.
Okay.
We can add a lot of strata, but is there a point where agent-based model makes more sense?
Yes. I mean, these models, I mean, I differentiated them or separated them into those 4 types, right? But the difference between the structured, the individual level and the agent-based is really a difference of degree, right? If you structure enough, you've basically got to an individual level model or an agent-based model. So yes, is the answer to that.
Okay, great. No more questions at this point.
Okay, I really need to get some water. I'll be 10 seconds. I'm just going to steal some from my daughter. Okay, there you go. I've got my Lake Louise, well, actually it's broken, but my Lake Louise mug from my daughter's bedroom. Okay, that's better. Right, so we may not overrun too long. I think I'm doing okay. Oh, look, my wife's brought up a cup of water for me. She's watching this downstairs. Thank you. All right. So, yeah, finally, I'll talk a little bit about some work that we've been doing. I mentioned him already. So Mark, my PhD student, who I co-supervise with Herman Bakima, is really driving this, along with Ryan and Isabel, who are actually medics working on the front line. So they're actually in the emergency rooms, seeing the cases come in. What I'm going to talk about now is basically an age stratified model, which incorporates the contact structures between the age group. This is very early work. It's not been published. It spent a couple of weeks with a journal before being rejected, and then was too out of date. But it's morphed into another paper, the changes in which I'll talk a little bit later on. But anyway, this really Mark's work. But the basic idea was, when we're thinking early on, we knew that age for COVID-19 was an important predictor of likely symptoms. We also know in other respiratory diseases, in fact, lots of different diseases, that it's also an important predictor of the likelihood of transmission, right? This could be biological, right? So it may be that different age groups shed the virus at different rates, which means they're more, or if they shed the virus at a higher rate, they're more likely to pass on the disease. But it also could be because age groups mix in different ways, right? I've picked my daughter up from school before and found her licking the nose of her best friend. I don't tend to do that with my friends very much. So age groups do mix in different ways as well. So we thought, well, let's stratify this model by age and concentrate on the contact structure. So first off, in the original model, if we go back to that, our rate of infection was, well, that's not actually the rate of infection, that's the incidence rate, I should call that, was defined as beta times S times I, right? So this was the thing that's really driving the infections. Now imagine that we stratify our population like we just did with males and females, except now I'll do it according to age class. Okay, so I'm going to identify the age class by a subscript K, going from 1 up to C. So I've got capital C age classes. I now need to divide the compartmental frameworks into an SIR compartment for each age category. Once again, these could represent, well, here they represent proportions. They could represent numbers of cases. But so we have S1T, I1T, and R1T for age category 1, going all the way down to SCT, ICT, RCT for age category C. Okay, so these are representing the number of individuals in each of those compartments in this age, okay, or proportion I've written down here. All right, so we stratified our model, and actually, well, no, I'll come on to that on the next slide. So the other thing we're going to do, we'll assume that susceptible individuals in each of those age categories can be infected not only by individuals in their own age category, but other age categories, right? Which is obviously realistic. 46-year-olds like me don't only mix with 46-year-olds. I have a couple of kids who are certainly in a different age category. So we want to allow that mixing between the different categories. But we will allow the rate of transmission between the different individuals, between individuals within different age categories to differ. Okay, so I'll define an infection rate or transmission rate, beta ij, and that represents infection occurring from age category J to age category I. Okay. So then the overall, I've been calling it infection rate, it's really incidence rate, to be clear. The overall incidence rate for susceptibles in age category I will be given by this, right? I'm going to sum over all the age categories. I have a transmission rate, beta ij, for each of the age categories coming to susceptible age category I, or susceptibles in age category I. My incidence rate is going to depend on the proportion of susceptibles in my age category, and it's going to depend upon the number of infections or the proportion of infections in all of the other age categories. Okay, so if I sum over this, I get an incident rate for susceptibles in age category I. The next thing I'll do is, just for simplicity here, I'll assume that the recovery rate is the same across age categories. Okay, and that leads us then to a new age stratified model, which looks quite similar to the SIR model I had before, except now it's in terms of the individual age strata, and the incidence rates are summed over all of the different age categories. Okay, the recovery rate is dealt with in the same way. Okay, so now I've gone from having 3 of these equations to 3 times C. And actually you could see, if you want to go back to the sex stratified model, you can see what that would look like in terms of the differential equations by thinking about C being equal to 2, or what it could potentially look like. Okay, a little bit more water.
So Rob, there is a question regarding the treatment of age. So if somebody wants to use age as a continuous variable, will this age stratified SIR model be used?
So you can do that, but then I would say, yes, you are really into an individual level model at that point. I don't think you can write that as a nice, stable series of ordinary differential equations. But you can certainly do it, and I'll talk, if I have time, which I hope I will talk about that a little bit at the end of session 2, about how we can make these incident rates individualized across the whole population.
And then there's another question on age. How is aging handled with an age stratified model?
Aging.
Aging.
So in this model, we don't consider it at all. I mean, essentially, it depends how far you're forecasting forward. So you might want to incorporate that, right? Because there will be people who move age categories as time goes forward. Mark might be able to put a comment up about this, but I'm pretty sure we're not incorporating that here. But you could incorporate it, right? You could have a rate of transition from susceptibles of age category 1 to susceptibles of age category 2, etc., etc. I think it would have negligible effect unless you're simulating for decades, right?
Thank you. No more questions at this point.
Oh, okay. So I've got my new series of ordinary differential equations, 3 times C of them, but I can just put those into the R code we saw before. Obviously, I've got a lot more parameters to worry about, but I can run that system, right, if I choose values for my parameters. But what Mark did was actually take this a bit further and try and incorporate some demographic information about contact rates between the different age groups. And this was really essential to trying to mimic social distancing policies. So what we did, or what he did, was he set this Bij to be equal to a beta times Cij, where Cij is a rate of contact between age categories I and J. I think actually in our model, it's not a rate, it's the number of contacts that someone has, but you could think of it as a rate if you wanted to do that. Okay, so what are we doing here? So basically we're splitting that Bij there, which is, you know, a function of both how transmissible the disease is between individuals and how much the population mixes into 2 component parts, right? So our hope is that now the beta there is really containing our information about the transmissibility of the disease, and this is containing information about the ecology, the population mixing, right? Okay, so we would then plug all of those into these differential equations, of course. The C itself, theCijs, the mixing, well, there's a paper of a few years back by Prem et al. In PLOS Computational Biology, where basically what they did was they took age stratified demographic data, okay, so the distribution of the population in different age categories, and contacts, smaller subset of the population, into an age stratified contact matrix. Okay, and I'll show you what that looks like. Oh, it's on the next slide. I'll show you what that looks like on the next slide, right? I said here they did it for the US and Canada. Actually, they did it for lots of countries. We're just using the US results here, right? So this was a Bayesian hierarchical model that sort of incorporated those 2 sources of information, the census demography data or age distribution data, and then the contact surveys to estimate what those contact matrices look like. We then went so this is a thing that statisticians don't do, but mathematical modelers, which I don't consider myself one, but mathematical modelers do all the time, which is that they got the estimates of those epidemiological parameters, or what we did, from the literature. Okay, so parameters, the transmissibility rate, the recovery rate, things like the mortality rate, that all came from the literature. And this is sort of important because we really didn't have the data to try and fit these models to estimate those parameters. And one of the nice things about the mechanistic model is because those parameters are biologically or ecologically interpretable, you can do piecemeal studies to try and estimate them, okay? But anyway, we got them from the literature. Obviously, then you need to do a sensitivity analysis and that sort of thing. But that's where those parameters came from. So what I'm describing here is mathematical modeling. It's not statistical modeling. This is not heavily tied to data, or not directly tied to data. We can then run our system of equations using the DE solve, but we can simulate the effect of social distancing measures by changing that contact matrix, which describes the rate of contact or the numbers of contact between the different age categories. So first off, I'll show you what the data looks like. So this is the contact matrix for Canada. So actually up here, we've got the age distribution, okay, stratified by males and females. So that's one of the components that goes into this. And then the method that Prem et al. Came up with, which I didn't mention previously, but is actually key for us, is that it separates contacts, or enables us to separate contacts into those that occur at home, those that occur at work, those that occur at school, and all of the ones left over, to give us an overall contact matrix here. Okay, so if we look at the school one, you can see things going on that make sense, right? We've got lots of people in the lower age categories mixing, and this is obviously school up to high school, or even university, well, high school, I assume. But you can also see that there's some mixing with the pupils and the teachers, which you would expect, right? But not the other way around, because well, it's not symmetric, okay? Similarly, if we look at home, you can see that there's a lot of mixing between people of similar age categories. Well, that makes sense, because we tend to marry people of similar age. If we have a flat share, we tend to share with people of a similar age, etc., etc. But then there's also mixing going on between what we assume is parents and kids, right? So that and the wider population as well. But anyway, so their method allows the contact between these age groups to be separated out and then recomposed or recombined to get a final contract, an overall contact matrix down there. Now this is really nice, because it means if we want to simulate shutting down schools, we just change all these to 0. Okay, if we want to simulate 50% of people going to work, we just half all of those. Okay, so it enables us to think mechanistically, that word again, mechanistically, about what's really going on in the population. Okay, and then to finish off, and I can't believe I'm almost on time, I'll just show you some output from like I said, this was an early incarnation of the model. So what we were doing back then was simulating across Canadian and US cities. And you can see here the epidemic curve. So for Chicago, under differing mitigation strategies, right? So I think actually this figure text is wrong, but you can see the red there is unmitigated. Then we have strategies like no school and work and other contacts reduced to 75%, no school and work and other reduced to 50%. There are actually more strategies down there than there are lines. So there's a mismatch there, but it gives you an idea of the sort of things we can do. The things that Mark primarily has done since is he's changed this model from an SIR model to an SEIR model. And he's also made the contact matrix dynamic. So we're now incorporating Google mobility data, so we can try and mimic what's actually going on in the population, and then project forward what happens when you lift these strategies, the social distancing policies in different ways. Okay, there are limitations to the model, so we have no migration in the model. We're assuming a closed population. In terms of births and deaths, that's probably fine, because it's I think that's going to be a low number. In terms of people coming from other cities, that's probably more problematic, and would definitely be more problematic as, borders are opened and that sort of thing. But the idea here was just to give you a flavor of the sort of things that you can do with these models. Oh, and there's one last slide. So they're detailed are the parameter values that we've used and some of the assumptions under the model. Okay.
Yeah, so Rob, can you show the previous slide? There was a question about what day are we at now, and which curve most realistically represents the level of social distancing imposed by the government.
Okay, so this was work that was done back in early April. So this is not, I mean, I don't think that, well, the red curve there, which is basically our best guess at what would happen if there were no control at all, right? The other curves were various mitigation strategies. I mean, Mark could better answer this in terms of which one is most like what we have now. I think a few things have occurred in that I think the social distancing policy has been more successful and more adhered to than we were assuming back then. Certainly more than I was. I think the rest of the group would feel like that. So I can't really answer the question of which is more realistic. In fact, you can see that all of these curves are actually overestimated. Well, actually, where are we now? We're on about day 100, right? Or day 120 or something. So yeah, these curves have overestimated, even in the most severe control strategies, what has actually happened. Or maybe not New York. Can't remember, what were the case counts in New York? I don't remember.
So there is an answer shown on the Q&A. We are about day 80 since reached 100 cases.
Day 80?
Day 80 since reached 100 cases. Quan was typing.
Sorry, can I see this? So you're saying on day 80 we did reach 100 cases?
No, we're about day 80 since reached 100 cases. 82 to be exact. Okay. I follow a dashboard. Yeah. Mm-hmm.
Okay, for some reason I can't see this. But okay. Okay. I mean, okay. I mean, there is a question, and I think this was part of what was just being asked, of what is day zero, right? When, or day one, when did this actually occur? And we don't know the answer to that. We don't know when in each city the first case came in, and we don't know how many unreported asymptomatic cases were in the population, or for how long before we actually started getting them reported. So we actually, and Mark spent a lot of time on this, tried to calibrate our model, the initial conditions of the model to sort of mimic the data, because there's a lot of uncertainty about how to actually start these simulations.
Okay, there's a quick follow-up on the question about this, which date we are with this figure. Is this the cumulative or the active cases? It's got to be active, right? It's not a cumulative. Yeah. Okay. So there's a couple more questions. One is for the dynamic context matrix. What resolution do you have? Monthly, weekly?
So Google mobility data is daily, but there's a lag. So well, at least last time I talked to Mark about this, they'll put up like a week's worth of data or whatever it is in one go. So if you're trying to forecast, that lag is slightly annoying. But no, this daily data, so we can see, when there's a fantastically warm weekend and everybody rushes out to the park, and the people who take their phones with them, which is most people, I assume, you can see that suddenly their mobility shoots straight up. As a whole, right? We're not seeing individual data, just aggregate level.
Okay.
Yeah,
So,
it's daily.
So the next question is that why this model use from the literature to derive beta, but not using beta directly from the literature?
Okay. Okay, I can't see the question, and I lost what you said then, Lei.
Okay,
sorry.
So why this model?
The Q&A button down at the bottom. There's something that says Q&A.
Oh, it's because I'm looking at the answered questions. I'm not looking at the open. Okay, thank you.
Use Arnold from the literature to derive beta, but not using data directly from the literature.
I don't really know the answer to that question, but if you've got an estimate of the infectious period, which gives you the infection recovery rate, and you have estimates of the R0, then you get to the beta, right? So I assume it's to do with either the papers that were available at the time or the papers that Mark took a fancy to. If you're there, Mark, please send something to the Q&A.
One last question for the moment. Could you please comment a bit on the comparison between the performance of the proposed method and the multi-stick model using individual level data?
Not really, because I don't have a comparison because we've not tried to do this with individual level data. So, or an individual level model. So the individual level model can be quite complicated, right? Can take into account who lives with who works with who, the distance between individuals, those individual level covariants, right? But in order to use that sort of model, we want two things. One, we want that sort of resolution of data to plug into it. And if you don't have that resolution of data, there's not much you can do, right? It doesn't, to me, it doesn't make much sense to make use a more complicated model where you really that you really can't parameterize. But the other thing is that the individual level model, well, actually I'm mixing up two things here, right? I'm thinking about the inference for the individual level model. When I'm using an individual level model, I'm generally trying to fit it to data. Despite the last 2 hours, I'm a statistician, right? And that's what I do most of the time. And that's very difficult to do in a situation where a large proportion could even be a majority of cases we never observe, right? They don't get reported, or they are asymptomatic. They may not even know they have the disease. So I don't really have a comparison. My broad answer would be that an individual level or an agent-based model has the potential to be more realistic, but it's more difficult to calibrate, parameterize.
Okay, so there's another question coming. Do you know if and how the data takes populations without good access to medical care and assessment into account?
If the data takes,
I guess, yeah, it's
so,
confounding and modeling.
So I think, so we're actually, another thing that we're doing at the moment is we're using these models for India. So we have some collaborators in India, which is, another project. And so obviously the data there is quite different from the data that we can get in Canada. So you obviously have to be aware of the quality of your data. You have to think about the differences in, population structure and that sort of thing. But you wouldn't, personally, I don't think you want to take exactly the same model and bung it into a completely different setting and assume that you're going to get, you know, decent output. If you've got a country where the contact or the mixing in the population is very different from the one you're originally working on, you'd want to allow for that somehow. So we allow for that using the global mobility data and the Premetal method to give us a baseline. So hopefully we can take into account differing contact structures in the different countries. If you didn't have that, you would at least want to change your beta in some way, I think, to try and allow for that.
Okay, I guess that concludes the morning session. And in the afternoon, we're gonna start at 2:30, and Professor Deardon gonna move to stochastic and Bayesian modeling. And Rob, do you have any parting words for us while we enjoy a late lunch?
No, not really. I actually, as you can hear from my voice, I think I need a little break. And yeah, I'm looking forward to actually talking about some statistics at a biostatistics workshop.
So Patrick, for those of us inclined to just stay, can we just stay online, or we have to log out, log in again? How does it work?
I would actually recommend staying online. Just mute your microphone if you want, and we'll be back at 2:30.
Sounds good.
Okay, great. Thank you.
All right.
Thank you. Yeah, thank you, everyone. Yeah, enjoy your lunch. And, see you in the afternoon.
Early lunch in Calgary.
Yeah. Oh, yes, yes.
No,
Sorry.
not for me. I'm a brunch type of guy.